All right. In the last class, we were going through electric fields, field lines, and then in the presence of dipoles, we found out how the field patterns were going with the identical charges, positive charges, and identical negative charges, and different charges. You could see how the field pattern was changed. And I also told you something about a null point. What's a null point? A place where there is no electric field. Or the net electric field is zero. That's possible. And so the idea of electric field is imaginary line drawn. Now, when you say imaginary lines, you can draw as many lines as you want, but there's something called flux. Now, some of you are still working on those questions. So, if you read through flux and all those things, you will be able to get it. But generally, what is this flux? Flux is how crowded the lines are. The field lines, how they're crowded. And what does that depend on? The flux depends on what factors. Okay? So there is a law based on this. Your exam and the final exam won't be using that law, but because it's part of this textbook, it's a good thing to know about it. So when you go to colleges and when you are going through what is known as Gauss law, you'll be wondering, like, what is that law? I never came across that in electric fields. So just be aware of it. That's why those questions are there. Now, Gauss law simply states this, that if you have a surface or something and if there is flux going out from it, how much is the flux that's going out from it depends on the electric field at that location and the area. Okay, how much flux is passing through a certain area? So if you have a certain area like that, how much flux is going through it? So the electric field was E, and if the area was A, then the flux that is going through, this is a symbol that is a Greek letter, is called phi. Mu, alpha, phi, and all those, different clubs are there, right? That's a phi they're talking about, phi, phi. Phi is equal to EA. And that's only if the electric field is intercepting the surface area perpendicular. You get it? If it is hitting it right perpendicular, then all the area is going to be passing those electric field, right? Now, since all the area is passing through it, that's why we take it as A. Now, if this thing is a little tilted, if that's a little tilted, so if I take this area, how much of this area can you see? All of it. If I keep it like that, it depends on your angle, right? How much of the area, you don't see the entire area. You see only a component of it. You see only a component of it. Now you see all of it. Now you see only a component of it. Now you see none of it. If it's flat, like that, your vision is going like this, and none of the book is visible to you, right? That sort of thing. So if I keep the meter stick, you can see the whole, like if I keep it like that, you're almost not seeing any area. Yes, there is an area here, but imagine it's a very thin material. If I hold it like that, you won't see, but if I hold it like that, you can see, right? So that's the idea of flux. How much is actually, like, you use the same symbol in magnetism as well later on. But magnetism, flux, we will, talk about it more. Electric flux is related to the Gauss law. And that is flux is equal to EA. Okay. Now, so if I have a charged plate, and if it's all charged, and flux is coming out from it, so if you want to know how much flux is coming out from it, you need to know how much is the electric field, and then times the area. If you know the electric field times the area, you got it. Or if you know the flux coming out from it and the area, you can find out the electric field strength. So that's why I said when you have a point charge, the flux is changing according to your proximity, right? So if I take a certain unit area, you can see the flux is less. If I take the same area here, the flux is more because the field strength is more. So over here the field is small and then the area is normal. Here the field is bigger and the area is normal. So you can see there's more flux here and there's less flux here. Make sense? So flux is basically the product of E and A. And now I told you the angle plays an important role. That's why we generally have the equation as EA cosine theta. Now what is that theta supposed to be? It's the angle made between the field lines and the perpendicular to the plane. The field lines and perpendicular to the plane. So if this is the plane, that's a perpendicular to the plane, right? What's the angle between your view and this perpendicular right now? 90 degrees or 0? 0. Your vision is this way and the north, this thing is also going straight. So the angle between your view and this perpendicular to the plane is 0. So we use cosine 0. And cosine 0 is 1. So you see all the area. On the other hand, if you do it like this, your view is coming this way. The perpendicular to the plane is going like this, so there is an angle. And that angle decides like, okay, that's why you see less flux here. This is trapping less of your vision. If I keep it like that, you don't see much of an area, right? That's because this is the perpendicular to the plane and your vision is this way. The angle is 90. Cosine of 90 is. That's why you have Gauss's law written in this fashion. This is how it is normally written down. But what's the maximum flux you can intercept from somewhere is when the area is completely exposed to the field, then you can get maximum. This is the maximum. Now, yeah.
So is the unit for flux like Newton meters squared per coulomb?
Yeah, this is Newton per coulomb and that is meter square, so you have to put them all together. Now, if you have a certain charge enclosed, suppose you have a certain charge sitting somewhere, how much is the flux that is passing through a certain area? So if this flux is going like that, how much flux is going at this location? So what do you need? You need to find out the electric field. What's the electric field at that location? What's the formula? K. I don't want K. I want the original formula. The original formula. K is just a shortcut, right? What's the original? Yeah, Q divided by the K is 1 over 4 pi epsilon, right? The K is 1 over 4 pi epsilon. So it's 4 pi epsilon. It could be epsilon naught or epsilon. So that is Q is equal to 4 pi epsilon. And what's the other one? The distance square, correct? So it is the distance square. That is your equation for E. And now, suppose I make a fence over here. I create a fence. And if I ask you, how much flux is actually coming out from that fence? I created the fence exactly at the location where the E is that much. How much flux is seeping out of that fence? Now remember, this is the electric field, and is it hitting it perpendicular? Yeah? So whatever electric flux is coming out from it has to go through. Has to go through. Even if I make it rectangular, it has to sneak through it. So the flux that is here has to go out. There's no difference. So it doesn't matter whether I'm making it oval shaped or egg shaped, nothing. This flux has to go. And the simplest fence you can actually think of is like draw a circle. Now, once you draw a circle, what's the surface area of the sphere? It's not a circle, it's a sphere, because it's a three-dimensional thing. So this is a charge Q, and I'm making this fence around it. What's the surface area of a sphere? 4. I'm not asking volume. Surface area. 4 pi r squared. Right? So if I want to know the flux here, the flux is going to be equal to 4, EA. And E is there. E is there, right? So EA becomes Q over 4 pi epsilon x squared times area. What is area? Now remember, the x is your radius. The x is the radius of the sphere. Yeah. 4 pi. And if you look at this equation, what's left? So Q flux is equal to Q over epsilon. Now, if nothing is mentioned about the space, if it is free space, then it will become epsilon naught. Now, if it is inside water or something like that, then you need to take that epsilon off water, which is epsilon naught, epsilon r. Make sense? So this is an equation that you will end up using for solving some of the questions. The question that you asked me? Yeah, so here is a charge, and then there is an enclosure. So how much is the flux going out? All you do is, how much charge is sitting inside? What's the net charge sitting inside? You may be having more charges, but what's the net charge sitting inside? That is this. And epsilon naught, 8.85 10 power minus 12. Finished. That's all you do. Get it? Now, if the net charge inside is 0, nothing. Nothing is inside, nothing can go out. Okay? Just keep that in mind. So you had some confusions. When you have confusions, the best thing to do is go to your e-textbook, read a little bit. You should develop that habit of reading something on your own and not expect it to be spoon-fed. Because when you go, next year, same time, you're in college. And you're listening to some lecture by someone speaking in some tongue. So is it possible that you understand everything that is being spoken? Are you really going to, is the lecture really patterned in such a way that you really understand stuff? Not necessarily. You'll have lots of gaps. You will hear some words which you have not heard before. So you have to do the research. You have to do the study and fill it all up. That habit should be developed already. So you'll see some questions here and there which are deliberately not explaining in class. But when you come up with some confusing questions, when you go to the e-text and read through it and find out if there is any symbol like that anywhere in the chapter, right? And then when you come up with the symbol, then you'll know what it is, and then finally you'll have ideas about what it is. So no matter what sort of shape you are putting it in, electric flux that can go out through a certain surface is EA. And in this case, it is simply that. So if you know the charge that is enclosed, just that. Okay? That will help you do that question. And between two electric plates, between two plates that are charged, so if you charge it positively and negatively, electric fields are going to be starting from here and ending there. And over here, since this side is open, the field will actually take a turn. And over here, it is all parallel and equidistant. The field here is called uniform field. This field is called uniform. And these edge effects are something that you cannot avoid. So if you have two plates, at the end you won't see a parallel line, it will be slightly bulged out. Okay? And that is an end effect. So where is it uniform field? It's all between these two, except at the edges. It's going to be uniform. So the value of the electric field here will be like 0, and then slowly pick up to a max, and then max continues to stay there, right? So that is the field between electric fields. Now what is this kind of field? What is that kind of field called? What is that kind of field called? What's that again? Radial, correct. That's a radial field. Because it follows the radius, right? Spreading out through the radius. That's called a radial field, which is not a uniform field. Uniform field is this. Why is it not uniform? Because E over here is big, and then smaller, and then smaller, and then smaller. Like the electric field kind of reduces as you go away. So the electric field is not uniform here. What is radial? If you have an electric field going like that, and if you put a metal box, what will happen to these electric field lines? As soon as it touches the metal box, the field lines will actually get diverted. So this metal box is going to bypass the field lines. So what will the field inside here? Nothing. The field lines will run along this path. There's no field inside here. Okay. So electric field inside is 0. That's what happens. This is called electric shielding. This is called electric shielding. Yeah.
Why would the field line, like the one at the bottom, return to where it was, the lowest field?
Because this is just a distortion. This is just a distortion created by this metal object. But after that, it has to return to normalcy because it is basically a continuation. Once it goes off from here, because this one repels it also. There's a mutual. Each one is repelling each other as well. So it won't stay there. It's like, you're running a cross-country race. Like many of you are running together like that, and there comes a puddle. So there's a puddle over there. You're not going to just march through it or run through it. So what will happen is like there will be a little squeezing effect. But will you stay like that always? No. Because when you squeeze, it doesn't feel comfortable, so you start coming back to your normal place after the puddle, right? The same thing happens here. Electric fields, they have to push out due to compulsion here. But after that is over, the electric field lines repel. You understand that? Electric field lines, which are going the same direction, they actually repel each other. That's why they kind of spread out. Yeah, they don't come together. Field lines that are in the opposite directions, they can slightly get attracted. Yeah, any questions? Yeah.
So matter if the box conducts electricity or not, you say no, it's not.
No, it has to conduct electricity.
Okay. And if it doesn't,
What's that again?
what happens if it doesn't conduct electricity?
It will pass through to some extent. It may get slight effect because even if it does not conduct electricity, it can get polarized to some extent.
Okay.
So once it gets polarized to some extent, it will create a little reduction, but it is not. Yeah. Any other questions? Feel free to ask questions. Yeah. So if I take my cell phone and put it into a metal box, just a metal box, I put my phone inside, close it. You can't call it. If you call it, signal is not going to go in. You can just shield it completely. So you don't have to turn it off into a metal box. Over. But what happens is the signals that are coming in, they're all electromagnetic, right? And remember, this also applies to magnetic shielding. You can magnetically shield something all all that is required is just a metal cage. You can magnetically shield stuff, protect stuff. Because the magnetic fields, if it is let out, it can actually cause problems to some equipments. So best thing is to put in a metal cage and boom. You're trapping it all in. It cannot go out. And nothing can go in as well. So if my cell phone is inside, it won't ring at all because what happens, signal bypasses and then goes off. Now, more effect will be if it is grounded. If I'm grounding the box, then it is going to go through it and then into the ground. That means you're losing the signal altogether there. That part of the signal is completely gone. It's going to the ground. It's just drained out. So signals can be affected in multiple ways. Now, when I started here, Dr. Zender was always telling me, can you make a jammer? So a jammer to jam the phones because he was frustrated by the students kind of using their phones, and he didn't want those phones to get the signal from outside, so he basically wanted to jam it. I said, I can make it, but it is illegal, and therefore there is a problem there. So it's not a big deal making it. You can make it. There are many problems involved in that. One, it is illegal, so it is something that I don't want to. Second thing, where am I going to keep it? I'm going to keep it more close to me. You come once in a while into this room, but this is going to be on all the time. So think of how much radiation I'm going to suffer because of that practice. No, I don't want that. So basically what's happening, what is a jammer? A jammer is a device that throws out thousands of signals of different wavelengths and different frequencies. So what happens is your cell phone is trying to catch one frequency from your tower, and when thousands of signals are going into that area, your phone cannot receive that one because it's confused. It's like this. I'm trying to talk to Adam one-on-one, and suppose you all decide that communication should not go on. What do you do? You'll start yelling different things, and then I'll be finding it so hard to communicate because he won't understand what I'm saying. I'm saying something, but he can't understand because lots of signals are getting into his ears. That is called jamming. You can jam that part of it. So when a cop is trying to get your attention, like finding out your speed, so he throws some electromagnetic waves at your car and it's supposed to bounce back from your car into his thing. So when that happens, if you have a jammer, which is illegal, okay? Don't follow anything that I say. Okay? That is illegal. So if you have a jammer attached in your car, what happens is his signal is coming to your car and bouncing off, but thousands of signals are also going to him. So his machine will totally not work because it cannot understand which signal is what. So wavelength and frequencies are all kind of messed up and different. So the instrument fails to read. But there's a danger if he thinks that, like, although he tried to do it, the machine did not work. So he might suspect that there is a jammer. But then you can turn it off. Maybe it's attached under your car, and you can turn it off, and then after that, he won't be able to trace you. But if you leave it on, he can actually figure out, where the signal is coming from, and then as it gets stronger and stronger, as he's approaching you, he will approach right to your car because the signal strength increases. So using a signal detector, they can actually come to your car straight away. There's a lot of things that are going on like that. Let's say I have a charge Q, and it is. Let's say I have a charge Q sitting on a sphere. So the sphere was initially uncharged. I have a charge plus Q, and I drop it on the sphere. So when you drop it on the sphere, what happens is the plus Q, where is it going to sit? Here, here, where is it going to sit? Everywhere. So it kind of splits off. It splits off and spreads out very evenly everywhere. Why it's even? is because it is spherical in shape, so it is supposed to be evenly distributed, pushed. It's like enemies put into a room, they'll try to go as far as possible. So this is what is going to happen, and the total charge that is there is Q, because that's what I put in. And now if I ask you, what is the electric field at this point? The radius of this one is R, and this distance from here to here is X. So what is the electric field at that spot? So to find the electric field at a spot from a spherical charged sphere, what we need to understand is this. How are the electric lines going to be from here? Is it going to be like that? Right? All the electric lines are going to be going out like this. That's how electric lines are going to be. But how to find out if at this spot, electric field? So for this, what you need to do is just imagine a little bit more. Imagine all this was concentrated in the middle. Imagine all of this, so there's no sphere, but it is just concentrated right here. So if it is concentrated right here, are the field lines going to be differently shaped? It will be identical, right? So whether the charges are sitting on the sphere, or if all the charges are sitting in the center, these field lines are going to be exactly shaped, same shape. Which means what? Which means standing here, looking that way, can you look at these arrows, the field lines coming to you, and say that yes, it is coming from the center? No. Is it coming from the surface? You can't differentiate. You cannot differentiate where it's coming from. And since you cannot differentiate where it's coming from, then it makes it easier. So then what you do is, consider all this to be concentrated in the middle. So if everything is concentrated in the middle, it will be like Q in the middle. And don't worry about this. This is the sphere. So charges are going to, the electric field lines are going to be shaped exactly like that. So from here to here, at this distance, how do you find the electric field? If the charge is sitting here, can you tell me the equation for this? K, Q, over, R plus X, or R plus X squared. That's going to be the electric field at that spot. The electric field is going to be that much. All you do is, don't worry about the sphere. Consider everything to be concentrated right in the middle, and just use the normal formula that you have been working with. Q, the electric field is K, Q over R plus X squared. Now what about inside here? Outside is that way. What is inside electric field? So what's the field right in the middle here? What's the field here? How do you find the field inside? What is the field inside? Q over? Let's see. Anyone else? What is the electric field right there? Remember the last day's lecture? 0 it is. Are there any field lines inside? There's no field line inside. There's no field line inside. You can see it's blank. Or if you want to think about, okay, how do you find the electric field? Put a unit positive charge, right? So if I put a unit positive charge here, will this push this? Yes. Will this push this? Yes. Will this push this? Yes. So won't there be a net field? There will be a net field, but that is 0. The reason is this. Okay, if it is in the middle, you can clearly say it's 0, right? Because this is pushing it, that's pushing it, this is pushing it, that's pushing it. But what about that point? Still it is 0. Why? Look at it. There are some charges in close proximity. And there are many charges with a greater distance. So eventually it cancels out. Mathematically it can be proven. But just think of this. Even if you are thinking about this, there are some very few charges at a close proximity, but there are majority of the charges at a greater distance. So they kind of cancel each other out. So the electric field inside everywhere is zero. Everywhere inside is zero in a charged sphere. Inside a charged sphere, everywhere inside the field is zero. You may have field outside, but inside is not there. And definitely you have experienced these things while you're driving your car and you turned on your radio, whatever, and you're driving through a tunnel. If you're driving through a tunnel, have you felt the radio reception is gone or getting weak? GPS is lost? That's because inside the field is not able to enter. Because when you're going through the tunnel, you're surrounded by soil, which is ground. Soil itself is the ground. So even if there were electric fields or electromagnetic waves coming in, it won't just enter the ground, because if it enters the ground, it is going to be grounded. So how can it enter your car? Now, in Dubai, there is one tunnel that is completely underwater. It's all completely underwater and ships are going about. It is just close to the sea. From the sea, it goes like that. It's pretty, they call it creek, but it's not. It's a wide creek. Okay? It's a big one. And almost in the entrance part of that creek, that's where they built the tunnel. The reason is because ships and boats and all that do travel. They come inside. So if you can't build a bridge and all that, is going to be tough. So they made this tunnel. And driving through it, it's kind of strange, when you drive and you just imagine that you're surrounded by water. What if this wall kind of breaks? So you just think like, oh, water is going to gush inside and you'll be filled with water and so on. That's what comes to my mind when I go through the tunnel. And normally the tunnel is very congested. It's not like a smooth flow. It's pretty congested. So when you're coming in like that, kind of sloped down, and then you are inside the tunnel. So water is all up there. And no radio signal, nothing comes inside. Nothing. Everything blank. No cell phone communication. And then you drive inside for quite a distance, and then after that it starts climbing up. The road climbs up, and especially when you have good amount of traffic jam, the climbing up is going to be slow, especially with a manual car that I was driving. It was a headache. Because when you have to keep holding the clutch and the accelerator in a balanced position. You don't want to roll back, so you just keep moving, and just, especially when the traffic stops, then you have to stop. But again, as you're stopping, you're kind of adjusting this, so focused on that part. It's not like an automatic car. So that is the only thing which I hated there. Especially when you're in a tunnel, already you're having some fear, and after that you just keep balancing on this. So till I get over to the top, I'm always like tensed. Am I going to roll back and hit somebody? Anyway, so the field inside was completely zero, because especially when surrounded by water, and that was salt water. Okay, it's zero. So the field inside is it. Now let me draw this in a graphical manner. Let me draw this on a graphical manner. This is distance. This is the electric field. And this is the center. The center right there. So how is the variation of electric field with distance? Starting from the center.
It decreases.
What is the electric field here, right in the middle?
Oh, nothing.
Nothing. What about here?
Zero.
Zero. So it's going to follow this. And that is the radius. That is the radius. So until here it is going to be zero. And as soon as you cross that shell, so from here to there, electric field is going to change. What's the electric field just outside?
A lot.
A lot. How much? E here is equal to KQ over R squared. It's going to be KQ over R squared. Make sure that you're able to follow all these things. That is KQ over R squared, which is the highest. And over here it's going to be KQ over R plus X squared. So what happens at this point is that the electric field shoots up to KQ over R squared. And since it is an inverse square relationship, the field kind of fades out like that. So at that spot, it's going to be pretty small. So this is a fluctuation of how the electric field is from a charged sphere's center and outwards. Now let's work through some questions. Some of the simple questions on electric field is basically to find out where is the null point. Where is the point where the net electric field is zero? Just like how I did for force. Where is the net force zero? And then we did a problem where can I put a third charge? Or where is the point next to these two charges where the net field is going to be zero? So you do exactly the same thing as what you've done earlier, but you won't have a third charge, but instead just a point. Get it? You know what I'm talking about. So if you have a charge here, and if you have a charge here, where is the electric field zero? So you don't have to bring a charge Q, instead you bring in unit charge. So bring in 1 coulomb, and then find the forces on it. So basically you're writing down the electric field from here to this, so I'll call it E1, from here to here, that is E2, and then, so instead of F1 equal to F2, you're just writing E1 equal to E2, not a big deal at all. It's exactly identical to what you've done earlier. And if I throw some charges at the corners of a square, so if I have Q1 here and Q2 here and Q3 here, and I tell you find the electric field at this location. So what you have to do is to find the net electric field there, so you just put plus 1 coulomb there, find the force from here, find the force from here, find the force from here, and resultant. Find the resultant. So process is exactly the same. And they may ask you different other questions saying, how many electrons need to be removed or added? So what do? So if I give you the charge, so if I say this marker was uncharged, and now it has this much charge. So if I say this one now has a positive 10 nanocoulombs, how many electrons were added or removed from it? Is it added or removed? This is a positive 10 nanocoulombs. Removed. How many electrons? So what do? Take the 10 nanocoulomb and divide by 1 electron's charge, 1.6 10 to the minus 19. And you'll get the number of electrons that were transferred. Okay? Keep that in mind. All right, here's a question. Let's see if you are able to get it. Two small non-conducting spheres have a total charge of 90 microcoulombs. Two small charges, Q1, Q2. The total charge, Q1 and Q2, the total charge is 90 microcoulombs. When placed 1.06 meters apart, the force each exerts is 12 newtons. When it's put 1.06 meters apart, the force each one experiences is 12 newtons and is repulsive. What does that mean? And the total of Q1 and Q2 is 90 microcoulombs. So what does that tell you about the charges?
They're the same charge and about the same.
Are they positives or negatives? They're both positives because if they were negatives, this would have come minus. So they're repelling each other. That could mean it could be positives or both negatives. But if both are negatives, that is not possible. And so repulsive, that. Now, if it is attractive, then what? One is positive, one is negative. Which means you're adding actually a positive one and a negative one, and I'm getting 90. Which means one of them, the positive one is definitely a bigger one, and the negative one is a smaller one. That's why the total comes, right? So you have to make those logical conclusions as we go on like this. And the question is asking you to find out what each charge is. What is Q1 and Q2? They want to know what is Q1 and what is Q2. So to find Q1 and Q2, you start from there. 12 Newton force. That's experienced. So what's the force experience formula? K right? That's a force expression. Substitute. 12 newtons is equal to 9 10 power 9 Q1 Q2, which we don't know, divided by 1.06 squared. So you just use their data and find out what is Q1 times Q2. Can you tell me what is Q1 times Q2? Use the calculators quickly. What is Q1 times Q2? One point.
4 times 10 to the negative 7.
What's the next digit?
1.41.
You sure about it?
$1.49.
Says 1.5.
This
10 power of
negative 9.
negative 9 coulombs square. It's coulomb square. Okay. So Q1 times Q2 is this. And you know Q1 plus Q2 is this. So let me simplify this. This is 9 times 10 power negative 5 coulombs. And this is 1.5 times 10 power negative 9 coulomb square. So you got this and you got that. Can you find out Q1 and Q2? What approach are you going to process with? What's your best approach? What do you want to do? You got the product, you got the sum. Can you find Q1 and Q2? What do you do?
I should just say like Q1 equals 90 minus Q2.
You can do that. Q1 is equal to 90 minus Q2, or this one minus Q2, and then substitute and work it out. That's fine. But it'll turn out a quadratic equation most probably. And then you have to solve for the quadratic equation. I'll show you another method which is much simpler. I will do a different approach. For that I use some algebraic expressions. Do you know what this is? What is it? A square plus b square plus 2ab. Now, what about this? A square plus b square minus 2ab. What about when I subtract those two? We have 4ab. So now you have a product, you have a sum, and you have a difference. Can you see that? So let me put it in terms of q's. Q1 plus Q2 squared minus Q1 minus Q2 squared is equal to 4 times Q1 Q2. So if I plug this here, and if I plug this here, can you find Q1 minus Q2? Go ahead. So this is 9 times 10 power minus 5 squared minus q1 minus q2 square is equal to 4 times 1.5 10 power minus 9. Shuffle it up and get q1 minus q2. This is going to be 8.1 times 10 power negative 9. And if I bring this side, it will be 6 times 10 power negative 9 is equal to q1 minus q2 squared. Now you can subtract these two. So it is 2.1 times 10 power negative 9 is equal to q1 minus q2 squared. So what is q1 minus q2? Just take the square root of this. See, there's not a big, we just use the sum and the product because that's what we have here.
4.58 times 10 to the negative 4.
4.5 times
10 to the negative 4.
4? 5?
Yeah, 4.58 times 10 to the negative 4.
4.58 times 10 power negative?
Yeah.
Alright. I bring that and put it here. So q1 plus q2 is this. q1 minus q2 is 4.58 times 10 to the power of negative 5. What can you do to eliminate one of them? Just add them. So what is 2q1? 13.58 times 10 to the power of negative 5. So what is q1? Six point. So we got q1. Now what you do is just take the other part. So this is 67.9 10 power minus 6 and this is 90 10 power minus 6. So you can find out what is q2. I feel this approach is much easier than taking a quadratic equation and all those things. I didn't do anything at all here. I just used this expression and got q1 minus q2 and went there and solved it simultaneously. Straightforward. The only thing we did was a square root. That is the only thing we did. That's an easier approach of doing that. All right. Another one. Now, in the same question, if they say it's attraction, then understand that the charges are going to be one positive and one negative. So you have to be a little careful in dealing with this. But yeah, this approach can get you there. But if it is positive and negative, you may have two answers, basically. I'm trying to get you some of the tougher ones, so when you go through the easier ones, you should be fine.